Hello everyone, welcome back to It's Tech Time. This is video 3 in my CCNA course. In this video, we will discuss the networking models OSI and TCP IP. If you don't know what those are right now, don't worry, we're fixing to get into it in detail. So you may be wondering what exactly is a networking model. A networking model is something that categorizes and provides a structure for networking protocols. For example, Ethernet. If you remember from the previous video, protocols are a set of rules defining how networking and devices and software should work together. TCP/IP is a networking model and OSI is also a networking model. So why exactly do we need a networking model? Standard networking models are used to ensure that different devices are able to communicate with each other regardless of the manufacturer or the company that they are from. Some examples are a Mac and a PC can still communicate and can still work together even though they are from two different manufacturers. Some examples of phones are an Android and Apple can still work together. OSI stands for Open Systems Interconnection. The OSI model was created by the International Organization for Standardization, or ISO. The OSI model standardizes the different functions that are in a network. As you can see from this diagram, there are 7 layers altogether: application, presentation, session, transport, network, data link, and physical. But even though there are 7 different layers, they all work together to enable different network devices to communicate. So if we start from layer 7, application, the application layer is what the end user sees. The application layer is what is interacting with software. For example, if you're viewing this YouTube video on a web browser, Firefox or Chrome for example. It's important with the application layer that you think of the protocol that is being used, not the actual app. For example, think HTTP or HTTPS, not whether it's Chrome or Firefox that you're using. A couple of functions of layer 7 is identification of communication partners and the synchronization of the communication. We'll go into detail about how this works. So here we have 2 representations of the OSI layer stacks, or in other words, 2 computers that are about to communicate with each other. We have a software application, for example your web browser, interacts with layer 7 application, and it wants to send some data to the system on the right. This data is processed through the OSI layer stack, adding something to the data as it goes down the layers. Or in other words, this data is being encapsulated as it's going from layer 7 to layer 1. Because the original data is being encapsulated with the additional information that's added each time it passes through a layer. When it reaches the physical layer, it is turned into an electrical signal that is transferred to the other system on the right. Then the neighboring system performs the opposite process. Each layer it goes through strips off the added layer of information to the data until the data reaches the application layer on the neighboring system. This process of removing the extra stuff from the data that is added to the layers is called de-encapsulation. Both the de-encapsulation process and the encapsulation process are examples of what's called adjacent layer interactions. Or in other words, they're interactions taking place between each layer of the OSI model. But the interaction taking place between the 2 application layers on the 2 different systems is called same layer interaction. This same layer interaction is what allows the application layer to identify communication partners and perform the other functions associated with the application layer. Layer 6 of the OSI layer model is the presentation layer. The presentation layer translates the format used by the application layer into a format that can be sent over the network. For example, the encryption of data as it is sent and the decryption of the data as it is received. The presentation layer translates between different application layer formats as well. To summarize, the presentation layer translates the data into the appropriate format that's needed for the receiving machine. Layer 5 is the session layer. It controls sessions between communicating hosts. The session layer also establishes, manages, and terminates connections between the local application and the remote application. For example, the web browser you're using and YouTube servers. So far, we've covered the top 3 layers of the OSI model. From layer 7 to layer 5, we did layer 7 application, layer 6 presentation, and layer 5 session. So while it's important to know these layers for troubleshooting or for taking the CCNA, these layers typically only apply to application developers, specifically when they're making sure their apps work with different systems. As a network engineer, you need to know them, but you won't work with them on a regular basis. If we go back and look at encapsulation again, data that is created in the top 3 layers is then sent to the bottom 4 layers that actually do the job of sending the data over to the receiving machine. When the top 3 layers send data down to layer 4 will add a layer 4 header to the data. Layer 4 is the transport layer. The transport layer segments and reassembles data for communication between hosts. Or in other words, it breaks large data into smaller segments that can be sent over the network and are less likely to cause transmission problems if an error occurs. The transport layer provides host-to-host communication, which is also called end-to-end or process-to-process communication. Going back to encapsulation, data is prepared by the top 3 layers. A layer 4 header is put onto the data at the transport layer. At this stage, the data with the layer 4 header is called a segment. A good way to remember that it's a segment of the transport layer is that if the data is large enough, a transport layer will segment out the data, and each segment of data will have its own layer 4 header. This data is then passed on to layer 3, the network layer, where a layer 3 header is then added onto the data in the layer 4 header. Layer 3 of the OSI model is the network layer. The network layer provides connectivity for in-host on different networks. Layer 3 is where IP addressing takes place at. You've probably heard of IP addressing before. We'll go into a lot more detail on this on a future video. The network layer also provides path selection between the source and the destination. It is also important to remember that routers operate at the layer 3, the network layer of the OSI model. A way that I tend to use to remember this is that routers read the IP addresses. Let's review where we are in the encapsulation process. The top 3 layers create data. Data is then moved to layer 4, the transport layer, where a layer 4 header is placed onto the data, and at this stage we now have a segment. The segment is then moved to the network layer, or layer 3, where a layer 3 header is then added to the layer 4 header. And at this stage our segment is now a packet. A packet is where we have data, a layer 4 header, and a layer 3 header. And then this packet is then moved to layer 2, the data link layer, where a layer 2 header is added to the front and a layer 2 trailer is added to the back. So now we have a layer 2 trailer, data, layer 4 header, layer 3 header, and a layer 2 header. And this is at the layer 2 data link layer. Layer 2 of the OSI model is the data link layer. The data link layer provides node-to-node communications and data transfer between hosts. For example, a PC to a switch, a router to a router, or a switch to a router. Because the data link layer is next to the physical layer, it also defines how data is formatted for transmission. For example, if you're using copper UTP. Layer 2, the data link layer, can also detect physical layer errors that may be present. The data link layer focuses on the MAC addresses of devices as opposed to the IP addresses of the devices, which was covered on the network layer. Switches, for example, operate at the data link layer. Looking back at where we are in the encapsulation process, the top 3 layers create data. The data is then sent to the transport layer, layer 4, where a layer 4 header is placed onto the data, and we now refer to this as a segment. The segment is then passed to layer 3 network layer, where a layer 3 header is added. Remember, layer 3 looks at the IP addresses, and we now have what is called as packet, which is data combined with a layer 4 header and a layer 3 header. The packet is then moved to layer 2, where a layer 2 trailer and a layer 2 header is added to the packet, creating a frame. Remember, layer 2 looks at MAC addresses. Frame is the combination of a layer 2 trailer, data, layer 4 header, layer 3 header, and layer 2 header. Now when this frame is sent to layer 1, there's not an additional layer of encapsulation that takes place. This digital data is then turned into electrical impulses that are transferred from one host machine to the end machine. Layer 1 of the OSI model is the physical layer. The physical layer defines physical characteristics of the medium transferring data between devices. For example, if you're using cables, it'd be the specifications of the cables that you're using. The physical layer is where the digital bits are converted into either electrical for wire connections or radio for wireless connections. So now our frame, once it's at the physical layer, will be sent along the cable, if this is a cable connection, to the end host. And once it reaches the end host, de-encapsulation will take place. This is where all the added layers are stripped from the data. The data link layer, the receiving machine, will remove the layer 2 trailer and layer 2 header, and then it will send it to the network layer, where the network layer will remove the layer 3 header. Then it will be moved to the layer 4 or transport layer, and the transport layer will remove the layer 4 header. Then we will have our original data that was created by the top 3 layers of the sending machine, and that is the process of de-encapsulation. So let's review a little bit. We have the data that is created at the top 3 layers of the OSI model. Specifically, is created by the application layer. Then this data is sent to layer 4, the transport layer, where a layer 4 header is added to the data, and we now have a segment. Then the segment is transferred to the layer 3, our network layer, where a layer 4 header is then added to the segment, and the segment is now a packet. And remember, packets keep up with the IP addresses. Then this packet is sent to layer 2, or the data link layer, where a layer 2 header and a layer 2 trailer is added to the data, which gives us a frame. Data, segment, packet, and frame are all what you would refer to as protocol data units, or PDUs. So for example, a segment is what you would call a layer 4 PDU, or a packet is what you would call a layer 3 PDU. And just in case you were wondering, a layer 1 PDU is a bit, referring to the actual bits that are being transferred between devices. Here are some acronyms to help you remember the OSI layers, depending on which layer you want to go from, either from layer 1 to layer 7 or layer 7 to layer 1. I personally like going from the physical layer to the application layer, and my favorite acronym to use is please do not throw Sasha's Pizza away. Please is for the physical layer, do is for the data link layer, not is for the network layer, throw is for the transport layer, sausage is for the session layer, pizza is for the presentation layer, away is for the application layer. So please do not throw Sasha's Pizza away. And again, that's just my personal favorite one to use. Another one that I've heard used a lot goes from the application layer to the physical layer, and it's a penguin said that nobody drinks Pepsi. So again, if you're somebody that likes to use acronyms to remember the OSI layers, here are some of the most common ones that I found doing a quick search online. If you can think of any other good ones, feel free to post them in the comment section. Now the model you're going to see used the most often is the TCP IP model, and it's called that because TCP and IP are some of the foundational protocols that are used in this model. The TCP IP model was developed by an organization called DARPA, which stands for the Defense Advanced Research Project Agency. And as you'll see in a minute, TCP IP has a similar structure to the OSI model. However, the TCP IP model has fewer layers. And while the TCP IP model is how most modern networks actually work, the OSI model is what influences how network engineers think and talk and diagnose the network that they were working on. So here we have on the left the OSI layer model that we've been discussing, and on the right you have the TCP IP model. The first difference that should pop out to you is that the application, presentation, and session layers of the OSI model are all combined into one layer on the TCP IP model. Both the OSI model and the TCP model share the transport layer. The network layer of the OSI model is the equivalent of the internet layer of the TCP IP model, and the data link and physical layers of the OSI model are combined in the link layer of the TCP IP model. With all that in mind, it's important to know that often if somebody says they have a problem at the layer 7 or the layer 2 layer, they're referring to the OSI model, layer 7, layer 2, layer 6. So while the TCP IP model is the model actually being used in modern networks, whenever somebody is talking about the network, they typically are using the OSI layer model of layer 7 through layer 1. Here's a diagram I found online that demonstrates the data flow between host A and host B using the TCP IP model. So the application layer creates data. That data is encapsulated by the transport layer, the internet layer, and the link layer. Then host A forwards this data over the Ethernet to router 1. Remember that routers work at layer 3 and that routers only concern themselves with IP addresses. So all the router wants to know is the IP address of where the data is going next. So when the data gets to router 1, it is de-encapsulated at the link layer and then sent up the internet layer. The internet layer is where the router actually looks at the destination IP address to know where to send the data. So then it is re-encapsulated and sent to the link layer and sent back over the internet to the next router on its way to the destination. At the second router, the data is de-encapsulated again at the link layer and then sent up to the internet layer where it looks at the destination IP address, and then it's re-encapsulated, sent to the link layer. The link layer then sends it over the Ethernet to host B, where host B receives the data at the link layer, de-encapsulates it at the link layer, de-encapsulates it at the internet layer, de-encapsulates it at the transport layer, all the way back to the application layer, where the original data that was produced by host A is received by host B. Now we have successfully achieved process-to-process communication between the application layer on host A and the application layer on host B. Now this process takes place multiple times and very quickly, especially if this is something like a Skype call or Teams communication. This also shows the host-to-host communication that took place between the transport layers. The data was never changed at the transport layer on the two routers that did nothing but forward the data, almost as if it was direct communication between host A and host B. Thank you for watching. If you found all that helpful, be sure to hit the like button and the subscribe button down below so you'll know when future videos come out. If you have a question, feel free to leave it down below, or you can go to my website and send me a message. There will be a link to my website down below where you can find the slides that were used in this presentation. And remember, if you found this video helpful, feel free to share it with others.